Okay, so before continuing along with household magnets, I'll remind you that the fourth problem set is due on Wednesday at class time, and it deals with electric circuits, pretty much like flashlights. So what I left off doing last time, I talked about magnetic poles. The world of magnetism is very similar to the world of electricity. We'll see that they're actually totally related to one another. A key difference between magnetism and electricity is that you can't find any free magnetic poles. There are no subatomic particles that have been discovered as yet that carry with them pure North Pole or alternatively pure South Pole. So all magnetic things that show up in nature are if they're magnetic at all, they're magnetic dipoles or more complicated even than that. But they have no net pole. So magnetic dipole, just to remind you, is a system that has a North Pole and a South Pole. And if you add them up, so South Pole being negative North Pole, if you add them up, there's no overall pole. They're magnetically neutral. But they can interact because they've got this polarization, this magnetic polarization where you've got a separated north and south. All right? Any questions about just that part of magnetism? All right. Which sort of carried us along to things like, so why are there things that are magnetic like this? What's special about this piece of metal, because it is metal apart from the paint, that makes it magnetic? And it turns out that there are certain materials, a very small number of them, that are intrinsically magnetic. And where that comes from, finally, is the subatomic particles again. Electrons, we know electrons carry a negative charge. They're also magnetic, but they are magnetic dipoles. They have a North Pole and a South Pole. And that's associated with a characteristic that electrons have, which is that they're effectively spinning. The details of how an electron works, it's all in quantum mechanics. And so we'll sort of get to that later on when I talk about how LEDs work. But basically an electron, you can think of an electron not only as having charge, a negative charge, but also spinning. And we'll see that because of that spin and because of its electric charge, it consequently has magnetic character to it too. So it's got a North Pole and a South Pole. And you can think of it as spinning one of two ways. Remember the old days when I talked about this is angular momentum or angular velocity and angular momentum up. Remember the right-hand rule way back when? And this is angular momentum and angular velocity down. Well, you can think of an electron as having those two choices. It's a little more complicated than that in the details. But basically, it can spin one way or it can spin the other way. And so if you go looking at electrons, you'll find that they're in one of two possibilities. And with that direction of rotation goes the orientation of its little magnetic dipole. So the electrons that are spinning one way are North Pole up, and the electrons that are spinning the other way are North Pole down. Is that okay? I mean, some of this is, I do have to do hand wavy because it is what it is, and the details are messy. But that's the basic idea. And so as a result of electrons having a magnetic dipole, I should also say that other subatomic particles have magnetic dipoles too, but electrons are the ones that matter to us today. Because electrons have magnetic dipoles, when you assemble them together to make an atom, sometimes those magnetic dipoles cancel out. For example, when you put together a helium atom, if you remember helium, it's got two electrons. And when you assemble helium, one of its electrons is let's say spin up, and the other one's spin down. The two of them have their magnetic dipoles oriented in opposite directions, and their magnetism cancels. So helium, for example, is a very non-magnetic atom. It just doesn't care about magnetism. But some of the other atoms, well, if atoms that have an odd number of electrons, you can't have this a relationship where they cancel out, because you've got one left over if you try to play canceling games. So atoms with an odd number of electrons are always to some extent magnetic, and even atoms that have an even number of electrons, like, boy, I'm very careful. Iron should have an even number, but I can't remember for sure. We used to have a periodic chart up here. I can't remember. Oh, sure, iron has an even number. another random observation is the atoms that have an odd number of electrons tend to be rarer than the ones that have the even number of electrons for things having to do with how the atomic nuclei were assembled. So iron is a very stable nucleus, so it's going to be an even number of electrons. Anyhow, despite having an even number of electrons, they don't all cancel, and so iron is quite a magnetic atom. And some of the other atoms, but as you bring the atoms together to start making real things, an atom's an atom, but by itself, you rarely find atoms all on their own. Like there are a few of the noble atoms, noble gas atoms, like helium, neon, argon, that stay by themselves. But by and large, atoms like to cling to one another chemically. And when they do that, that glomming together process tends to cancel the magnetism. So that most of the materials, molecules, and finally grand substances that are made out of atoms have very little or no magnetism left. It's all canceled. And that's particularly true of organic molecules, most of what we're made out of. What assembles those atoms together, what holds them together, is the sharing of pairs of electrons, what are known as covalent chemical bonds, which you may have encountered in chemistry, that sharing of a pair of electrons. And with that sharing of a pair of electrons, you get one spin up, one spin down, and they're magnetically, they cancel. So almost all organic molecules are magnetically dead, nothing left. That's why you don't respond to magnets. I mean, you can put you in a strong magnet, nothing much happens. All right? So the rare exceptions, things like iron. Iron is the chemical. So a piece of iron, in principle, is just iron atoms with some degree of purity. Steel and iron aren't quite the same. Steel is predominantly iron, but other things are added to it to give it characteristics that make it, well, often more useful. For example, the most common thing that's added to steel, added to iron to make steel, is the chemical carbon, the element carbon. And iron and carbon have an amazing relationship as a pair of elements. Just a little bit of carbon turns iron into a much stronger material, that being steel. It's a whole story in and of itself. It's one of my favorite stories. I don't think I'll have a chance to talk about it in any detail in this semester. But basically, iron and carbon steels, the steels that are made just by adding small amounts of carbon to iron, they're magnetic. And to give you an idea of how that works, when the iron atoms go together and stick to one another, begin to make a bulk piece of iron, their magnetism does not cancel for interesting reasons. There's some cancellation, but a lot of leftover electron magnetism is present inside the iron or steel. And that's not true of copper or aluminum. I showed you a little bit last time. So this is a strong magnet, and aluminum could care less. The cancellation of electron magnetism is complete in aluminum. It's especially non-magnetic. Same with copper. If you want to make things that have no response to a magnet, copper and aluminum are really nice choices. Oddly enough, stainless steel, which is another variation on steel. Again, it's mostly iron, but it's got other stuff thrown in to give it interesting properties. In the case of stainless steel, those other elements are usually chromium and nickel, and not only do they make it more corrosion resistant, but they typically kill off its magnetic character completely. So a lot of the stainless steels are non-magnetic. There are magnetic stainless steels. They're chemically a little different, but don't look to stainless steel to make good magnets out of. So back down then to iron. So this is just a big chunk of iron. It has very little of anything else in it. It might be steel, but it's pretty much so nearly pure iron that I can call it iron. And it sticks like crazy to a magnet. Well, what's going on there? First off, okay, obviously it sticks like crazy to a magnet. Why doesn't it stick to other iron then? Do I have another piece of iron kicking around here? This is actually iron up here. It doesn't want to stick. This is also iron. Doesn't want to stick. So if you just find chunks of iron kicking around, they don't stick to one another, but they will stick to a magnet. And the reason for that is this. Iron is what's known as a ferromagnetic material. The people who study the magnetism of materials there are a variety of different magnetically interesting arrangements. Ferromagnetism is probably the most important of the bunch. What it means is that if you go down into a piece of a ferromagnetic material, and the one to choose to think about is iron. If you look at iron, you zoom in with a microscope, and you look down to the point where you're looking only at a couple of atoms, you'll discover within your view, not only are the atoms still magnetic, having not canceled all their all the magnetism associated with their electrons, but they agree about which side should be north and which side should be south. So that this little patch of material, atoms, might have agreed that we're going to have our north pole at this end and our south pole at this end. And while we have no net magnetic pole, again, they can't, we will have a polarization. North is up and south is down. That's typical of a ferromagnetic material. When you look in close enough, you find groups of atoms that agree. All their electrons are lined up right to all work together to make a big north pole at one end and big south pole at the other. But if you then move your view, again, still microscopic, you shift over, you look at another patch of atoms. They too agree on which side should be the north pole, which side be the south pole, but it's a different choice. It might be north pole over there to your low right and south pole up here to your high left. And what's happening then is that within this material, this overall piece of iron, you have patches, or what are called domains, in which there's a lot of agreement on which way their magnetic orientation should be. But if you look from domain to domain, they disagree. And sort of a way of visualizing that is this array. I've got an array of compass needles down here. We'll look down from above. And I'll put it over on that side projector this time, so I can leave my slides up there. Dun, dun, dun. There you are. Okay, so you're looking down at this array of compass arrows, and they are magnetic, actually, and they are lining up magnetically with each other. But you'll notice that there are patches. I should also say that there occasionally are compass needles that have been magnetized backwards, which is something I'll come to in a minute. So they are oddly pointing in the seemingly crazy direction. I'll look at this patch right up here. If you look at these guys up here, this little arrow has a north pole and a south pole, and that north pole attracts the south pole of its friend, which then attracts the north pole of it, which has another north pole at the other end, attracts the south pole of its friend. So these three arrows are all lined up with one another, as you might expect. They like that, and their nearby neighbors are doing the same thing. So here's a little patch of arrows all pointing the same direction. But very nearby, you get patches of arrows that are pointing in completely different directions. Why is that? Well, it turns out there's a lot of energy present. When all of them line up together, then the entire pack, the team, basically has a lot of north pole at the arrow end of the group, and a lot of south pole at the south end of the group, and that tends to want to flip individual arrows. Some of the arrows in a vast array, everybody pointing like this. One little magnet joining the team, coming in, goes, this is not good. I'm North Pole near North Pole and South Pole near South Pole. I would love to turn around and go back. Remember the goldfish cracker package with the one fish going backwards? Is that familiar to you all? The little atomic magnets want to turn around. and that's a process known as demagnetization, or spontaneous demagnetization. This whole group of magnetized, aligned arrows they get unhappier and unhappier as more of them line up. And so what's happened in this case is only small groups have lined up, but there are lots of separate groups, and they all disagree. And that disagreement gets rid of this energy associated with everybody lining up. And that is, so up there, there's no overall magnetization, which is to say there's no one side of that, or one area that is significantly North Pole and an opposite side is significantly South Pole. It's a big free-for-all fighting each other. That's the main point. And that's what happens when you just look at a piece of randomly chosen steel or iron. It's full of magnetic domains, microscopic regions where everybody agrees. But if you zoom out a little and look at a bigger patch, you'll find the domains all are fighting each other. And there's no overall decision that North Pole will be to the right and South Pole will be to the left. Is that okay? So that's why, for example, you can take some paper clips straight out of the box, brand new, and these guys are filled with magnetic domains. They're all randomly oriented, and they will not, therefore, stick to each other. The bottom of this paper clip is not a South Pole, for example, that will be attracted to the North Pole of another paper clip. They don't care. Well, how do you then make that magnetism, the microscopic magnetism that is present in iron, how do you make it noticeable? Well, you have to magnetize the iron. And you do this by forcing all the little magnetic domains to change so that they all agree. You break the stalemate and force them to go together. Typically, that happens by the growth of some domains and the shrinkage of the others. I'm going to get those domains to line up by magnetizing them with a real magnet that's got a very strong North Pole. So I'm going to take the North Pole of this magnet near those guys, and this is going to break their battle, and they're all going to notice this North Pole, and they're going to line up with their South Poles oriented towards my big North Pole. So I've got large patches lined up. I didn't get the whole thing's attention. Maybe with a bigger magnet, I can get the whole thing's attention. I got almost the whole thing. But this is what you do when you take a magnet up near your refrigerator. When you take a big, strong magnet, you take one pole of that magnet, for example, the North Pole of that magnet. You go up to the refrigerator, and all the little magnetic domains that are oriented correctly, that are oriented so that their South Pole is pointing out towards this approaching North Pole, they're happy. But all the domains that are pointing the wrong way go, I'm being approached by, there's a North Pole approaching my North Poles. I'm going to change and flip around, or the actual mechanism of that flipping is complicated, but they all turn around, and pretty soon, you're bringing your North Pole up to not a non-magnetic refrigerator or a demagnetized refrigerator. You're bringing up to a refrigerator that has been magnetized by your approaching magnet, and now they attract each other. It's a lot like the polarization that happened electrically with the balloon. When I took a charged balloon and held it near the screen, I caused the screen to become electrically polarized and attract the balloon. The same thing happens here. That North Pole approaching causes all the little arrows to line up. It creates a magnetic polarization in the iron, or these arrows, and then it's attracted. Is that okay? Are there any questions on that idea? You might wonder then, so once I've done this, oh no, I have magnetized that collection. Yeah. So, the magnetic polarization, is that a vector? The answer is yes. It has a direction to it. Yeah, it's an amount and a direction. So it points. Yeah? No. Do you need to know the unit? No. Just the fact that it happens. And you can see it always ends up as an attractive result. So when you magnetically polarize a piece of what was non-magnetic ferromagnetic materials. You know, it's got the microscopic magnetism in it, but it's hidden by randomness. When you line it up, it always lines up so that it's attractive to the approaching magnet, and the magnet sticks. It's never repulsive. Emery? What's with the ones that are facing the wrong direction? They're little compass needles that over the years have been magnetized backwards. If you take one of, because those little needles, although I'm pretending that they're little perfect magnets with a north pole at their head and a south pole at their tail, they're actually real pieces of iron. And it is possible to force them to develop a north pole at their tail and a south pole at their head. And we'll do that in a minute. And if I don't do it, remind me. They're all facing the same direction. It's just that, in effect, the labeling got ruined. Other questions? So these guys all lined up. And that suggests that if you take a magnet up to your refrigerator and you touch the refrigerator, that you line up all the magnetic domains in the refrigerator. It attracts this magnet. But what happens when you take this magnet away? Do those domains stay that way? If they stay lined up, the refrigerator is now magnetic, and it will attract other refrigerators. Well, usually that refrigerator loses its magnetism. And that's another story. It's the story of materials that are microscopically magnetic, that have magnetism hidden right down to the layer of the atoms. But you can magnetize them by bringing up a magnet nearby. The question is, what happens when you take the magnet away, the magnetizing magnet away? Do they forget? Do they go back to the way they were, or do they stay magnetized? And the materials that quickly forget that anything special ever happened are known as soft magnetic materials. They very quickly forget. And I think this piece of iron is such a material. So it's quite magnetic. It's quite ferromagnetic. That is, it's easy to get its attention and line it up. But when you take away the magnet that did the trick, that lined it up, it forgets. And so this guy has no effect on those. You know, there's nothing here. If I get it, I should, you know, there are thousands of things we could play with. If I bring the north pole of this strong magnet near this piece of iron, it will develop a south pole at its place closest to the north pole that I brought in. What's going to be at this tip now? A north pole. And it works, sure enough. It's a north pole there. But if I take away the magnet that did the magnetizing, this piece of very soft magnetic material is almost totally forgotten. Barely any effect. How about a situation where material that's not quite as good at forgetting? Well, paper clips. Paper clips, now we're getting, that was pure iron. And pure iron is actually very soft magnetic material. It just has almost no magnetic memory at all. As soon as, it's like Dory in Finding Nemo. Paper clips are made out of a steel that has little carbon in it. And the carbon makes it a little less soft magnetically. It's a little more of a hard magnetic material. It has a better memory. So I'm going to touch, I have just touched one end of the paper clip to the north pole of this magnet, and that means that I've developed a north pole at the bottom of the paper clip, and it can pick up a second paper clip. And that one becomes magnetic and get a third paper clip. And a fourth paper clip. Oops, can I get a fourth? Let's see. Yeah, okay. So I've got a chain of 4 paper clips. The first one, our fixed magnet, permanent magnet, we call it, is magnetizing the first paper clip, which is magnetizing the second paper clip, which is in turn is magnetizing the third paper clip, and all the way down to the fourth paper clip. If I take away the original magnet, they're still remembering it. Let's give them a little time. they will forget a lot, but it may take a little while. This is happening. Thermal energy is doing the scrambling. It's gradually wiping out the magnetism. We ought to lose that last paper clip. Come on. I'll cheat eventually. You may have noticed that magnets, if you've had magnets around, if they get too hot, and too hot's pretty hot from normal magnets, you ruin them. The thermal energy just kills off that organized arrangement of atomic magnetism. Well, I'm having trouble getting rid of it. I can probably wipe it out by that killed it. I jiggled this guy's magnetic domains a little bit, and the rest of them all got in trouble. Okay, so the point of showing you this is that there are materials that forget immediately. Those are the soft materials, and that's useful. In certain cases, you want things to forget quickly. In other cases, you want them to remember for a while, and the paper clips are decent. They're better than I wanted. I wanted them to forget better, but you get what you get. So that brings me to things like how, when you make a magnet like this, when it was first made, it was just a piece of ferromagnetic material. Yes, it had microscopic magnetism, but there was no organization. So there was no direction that had a big pole, north pole, one end, south the other. It was just nothing. So this was deliberately magnetized, and it is a hard magnetic material. So, and not very hard, it turns out. The cheap magnets are not really that good. So it was deliberately magnetized at one point to develop a north pole and a south pole, and it's still stuck that way. But we can unstick it. And to show you that, make sure you all can see. Let me just get this magnet out of the way. So right now, the red north end of the magnet in my hand is indeed attracting the south end of that swivelly magnet, right? So that really is a north pole. But that was created at a company. It didn't have to be the north pole. It could have been magnetized the other way, and we can magnetize it the other way. This is a magnetizer. Its only purpose is, and let's see, that's the north end. So I am going to put what is labeled by being red, the north end of the magnet, into the part of that magnetizer that will create a south pole. And having a second one of these, I'm going to put it in with its south pole in the place that will make a north pole. And I press the button, and the button imposes a huge magnetization on these guys. And I do it a couple times just to really get its attention. Okay. So now, this is the magnet I had a minute ago. And I'm going to see whether this is still the North Pole. No. Although it's labeled the North Pole, we have messed with it. We have turned all the domains inside this metal around. And so although it's labeled north, it's actually a south pole up there, and vice versa. So don't believe every magnet you ever encounter. When it says north, its history matters. If it was properly magnetized back at the factory, or most recently, fine. But you can mess it up, you can reverse it. And if any of you ever read Jules Verne's Journey to the Center of the Earth, their magnetic compass gets flipped during the course of the adventure. And suddenly they're going the wrong direction. So I want to remagnetize this guy correctly. And now, we're back to normal. The magnet is properly oriented. And so that explains why some of those magnets over there, why they're backwards. They had that nastiness happen to them where they were held in place, and the arrow tip was brought very close to a very strong North Pole, which reversed the magnetization in those arrows. And there have been times when we thought of taking these things apart and trying to fix all the arrows, get them all back to where they're supposed to, but it's not worth the trouble. And plus, they get wrecked again. Okay? So soft magnetic materials, strong magnetic materials. A few other things to show you that. I just want to make sure I'm not... two demonstrations I can show you. One is we can watch the domains flip, not with our eyes, but with our ears. There's a piece of iron right here that has just electronic sensors around it that's looking at its magnetization. And if I magnetize it one way, of course, all the domains have to line up properly to attract the approaching magnet. And if I reverse the magnet, all the domains have to reverse. They have to go the other way. Well, each time a domain reverses, we can hear there's a little tick in this audio system. And you can hear, it's going to sound like a wave breaking, maybe. I will reverse all the domains. They will not all go at the same time. So there's a whole series of ticks, and it sounds like it's a whoosh sound. Ready? Wait. Now I'm not getting any sound. Where's the sound? Oh. That should work. Come on. Rasm, frasm. I'm not hearing it. Whoosh, 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 whoosh. Oh well. Sometimes you win, sometimes you lose. I still have one more trick up my sleeve, and that is the magnetic stripe on your credit card. What is that? Before I say this credit card, all these permanent magnets that are around, they're just hard magnetic materials. Basically, many of them are just iron with some carbon in it. These are just carbon steel bars that have been magnetized. Your credit card has on its surface, I won't use my favorite credit card because sometimes trouble ensues. So credit card there. Oh yeah, my secret number. Okay, now I'm in trouble. There's a strip. Can you see the strip? It's not. Do I have a better, more visible one? Let's see. Give away all my money here. Nah, it's about as good as it gets. Okay, so that of course is the magnetic strip there. What is it? It's a strip of hard magnetic material. That is, it's magnetizable, and when you magnetize it, it remembers quite nicely. It was magnetized once by the company that issued that credit card. And if you want to see what that is, what the magnetization is like, you can put other soft magnetic material on top of it. Because the hard magnetic material being magnetized will polarize and attract any soft magnetic material you put nearby. For example, iron powder. So I'm going to sprinkle iron powder onto this, and I sure hope you'll be able to see it. We'll give it our best shot. I need to get a shiny reflection somewhere. And I'll zoom in. We'll get it. We'll get this. I can see it with my eyes now, but I expect to have my account wiped out by you all later today. All right. I'm just going to try to illuminate it. Of course, one time I don't have a flashlight. Gotta get a shiny spot. Somebody shiny. Come on. It's there. Where's shiny? Somebody have a flashlight? Sure. Let's try this. Thanks. I appreciate it. I normally have a flashlight, but I ran the battery. Come on. This is painful. There you go. Oh, there we go. I had it for a second. Operator error. Endless operator error here. Can you see those patches? There we go. Can you see those two stripes? And the stripes, I'm going to tap it some more. Those stripes actually have little patterns, little pattern to it. Can you see the pattern? Now I've got it there. The thick lines, thin lines, all in there. That's ions clinging to the regions between a North Pole and a South Pole. It loves those special spots. And so the data is written in that strip as the locations of the North Poles and South Poles in the strip. And that's why if you expose it to a strong magnet, and it turns out you have to expose it to a pretty strong magnet. Over the years, they've made these things pretty hard. It's very hard. It's not easy to erase that data. I mean, I can wipe this off and put it back. It'll work just fine. There would be no money there, of course, because you will have wiped me out. But what can I do? But that's what's going on in those magnetic strips. Anything else? Magnetic tapes I would have talked about years past, but magnetic tapes have gone the way of the dodo bird. You guys never encounter them anymore. Cassettes, like, what's that? 8 tracks? That's even before my time. All right. All right, I'm just going to go. Wait a second. Do I want to do that? Yeah, I'm going to skip that. Okay, about the Earth. The Earth is magnetic, and it produces, it's got a north and a south pole, but here in the middle of Charlottesville, when we go looking for that magnetic pole, we can either think in terms of the North Pole attracts the South Pole of the compass, and the South Pole of the Earth attracts the North Pole of the compass. Or we can do the same sort of thinking that we did when I was introducing electric fields. Remember electric fields? They appeared as an intermediary between two electric charges. Instead of interacting directly, the first charge creates the structure and space around it that is called an electric field, and the electric field, in turn, interacts with the second electric charge. And that seemed like a nuisance, and why do we bother doing that? But my claim has been that electric fields are real, and that leaving them out means leaving out a lot of understanding of how these things work. Same is true of magnets. You can think of two magnetic poles as interacting, say this North Pole and this South Pole, as interacting directly. This North Pole pushes on the South Pole, and the South Pole pushes on the North Pole. But you also can think of this North Pole creates around it a structure in space known as a magnetic field, which in turn pushes on magnetic poles, other magnetic poles. And so the magnetic field, again, it turns out that's real. And the Earth has a magnetic field, which you can think of as created by the North Pole and the South Pole. The Earth's North magnetic pole and South magnetic pole, they create this structure. When you look for the Earth's magnetic field here in Charlottesville, it turns out it's not just pointing northward, it's actually pointing north and downward. It dips into the Earth because the Earth is round and we're here on a portion of this rotating, this curving surface. The actual direction of the Earth's magnetic field isn't pure north, which is about like that. It's north and downward. All right? What else do I want to say? As with the electric field, magnetic field is a vector field, meaning it has a vector value at every location in space. There's a vector value here, which is the strength of the field and in which way it's pointing, and there's another value, vector value here, which is the mountain strength and so on, mountain direction. What else do I want to say that? Yeah, okay. the Earth's magnetic field is not quite perfectly aligned with the Earth's geographic orientation. Last I knew, the Earth's poles they're not perfectly underneath the geometric poles, and they're actually moving with time. And people have followed how they've moved over the centuries or millennia. Question though, how to ask you, I haven't asked questions for a while, but the Earth basically acts like a giant bar magnet. Okay, it's round, so it's got this complexity that you actually have to point not just straight horizontally, but a little bit downward. What's located at the Earth's north geographic pole? You hold your compass out, it points north, its north pole points north. What's at the north geographic pole? A north pole or a south pole? How many think that it is a south magnetic pole located at the north geographic pole? How many think it's a north magnetic pole at the north geographic pole? Yeah, you guys have it right. At the north geographic pole, or pretty close, is the Earth's south magnetic pole. So the magnets, your compass needle, its north pole does point toward the north, in effect attracted by that south magnetic pole up there. There have been a number of reversals of the Earth's magnetic orientation, of its magnetic polarization over the geologic time scale. For us, it would be a minor nuisance. All of a sudden, all your compasses would be backwards. There are animals that are able to sense the Earth's magnetic field, and it helps them migrate, for example. And I think it's understood that a certain fraction of, for example, migratory birds are backwards. They would by themselves migrate the wrong way because their magnetic sensor is reversed. And you need a couple of those sort of wrong way birds to deal with the reversals. So you're that real. So that's that. Okay, we have no one's ever discovered any magnetic sensor in humans as far as I know. All right. So last topic. I'm not going to get into electric power distribution today. This will do us. Last topic is we've seen these magnets that arrived here already magnetized, or these magnets that I can magnetize with an already magnetized magnet. But there are also magnets that can in fact magnetize themselves using electricity. Where's that from? And it turns out, so-called electromagnets, it turns out that when a current is flowing through a wire or anything else, that current is magnetic. Currents create their own magnetic fields. And this is the first, I think this is the first case where electricity and magnetism have suddenly drawn together and are starting to share turf. Up until now, the world of electricity has been charges interacting with charges, and they have electric fields and so on. And the world of magnetism has been magnetic poles interact with each other, and they can move around and all that stuff, but it's all magnetic. Here's the first case where we're crossing the boundary. A current of electric charge, which is to say electric charge that's moving, is magnetic. And so if you send electric current through a wire, that wire develops a magnetic field around it. Depending on how you arrange it, the field can be strong or weak, and it can also magnetize ferromagnetic materials that are near it. So here's an example. I'll just plug this in. So this guy, this big structure here, right now is not magnetic. This is a big chunk of iron. Those are chunks of iron. They're actually all soft magnetic materials. They've completely forgotten magnetism. They don't care about it at all. But if I run an electric current through these coils of wire around the base of these horns. So I'll run that current. Okay, it's running now. This, you can't pull this off. I mean, you can't do it. And if it flips over like this, you really can't do it. So this is now by far the strongest magnet in this room. It's really crazy. Magnetizing all this stuff, it turns out, took energy. And that energy is now here in those magnetized things, or equivalently in the magnetic field that I've created here. If I stop this as being a magnet, which I can do by opening that switch, all the energy that's in here leaves. And it's going to leave right in the switch. Watch the switch. Okay? That was the energy coming back out. Now, no problem. Turn it on. Clunk. No way you can get that off. Okay? So that's one version. If you want to play with it, stay away from the wires, and don't get yourself pinched. Bad, bad news. So that's one electromagnet. The other one's up here. No stairs. Got to do it myself. All right. More soft magnetic materials. No memory of any magnetism. But if I put them on, flip the switch, supposedly, make sure I don't bust my knees up, okay? Woo! Okay? And if I turn this off, it has a little bit of forgetting time, forgotten. Okay? So it's an electric current. In both these cases, it's an electric current that creates its own magnetic field, which then magnetizes the ferromagnetic iron, very soft material that has lots of magnetic domains in it, but you've got to get their attention, get them all to agree. They agree so strongly that that magnet attracted this magnet, polarized it, to polarize each other and stuck enough to hold me up. Any questions about that idea? I think I've got one last slide. Just to give you a preview. Up until this last observation that currents are magnetic, we've had the world of magnetic fields and the world of electric fields. Magnetic fields up until this point were created by magnetic poles or subatomic particles that have in effect magnetic poles. And why do I have moving electric charges here? This is a new one. That you can create magnetic fields with moving electric charges is new, yes. Electric fields up until now have been produced only by electric charges and subatomic particles that, in effect, carry electric charge. But pretty soon we're going to see there are other ways of making electric fields as well. So what this view graph is trying to show you, slide is trying to show you, is magnetic fields can be produced by things other than magnetic poles. Electric fields can be produced by things other than electric charges, and we're just starting to get there. Our first entry in the table beyond magnetic poles and electric charges is that the magnetic fields can be produced by moving electric charges. All right, so we'll call it a day, and on Wednesday I'll start looking at using this relationship between electricity and magnetism to move electricity from long distances through power lines.